Good morning, everyone. My name is Cindy, and I'm happy to be here today with my colleagues, Cynthia, Morris, Marco, and Sunny, to present on TLS. We'll be covering some key topics, including TLS 1.2 and TLS 1.3. We're looking forward to sharing what we've learned and hope you find it informative. We thank you in advance for your time. I will start with my section first, TLS 1.2, when leveraging RSA key exchange. I thought it would be a great idea to start with an example of Alice and Bob, because we all know how much Professor Barbara loves Alice and Bob and examples of them. I'm just kidding. Now that I have your guys' attention, we'll hop into the real fun stuff. All right, let's just start right to it. As we know, TLS Handshake involves several exchanges between the client and server. First, it chooses a protocol TLS version, then it selects a cipher suite. It verifies each other by exchanging and confirming digital certificates, then creates session keys to use symmetric encryption after the handshake is complete. Some important key takeaways from the handshakes are cipher suites. Cipher suites are used to create a secure connection between a client and server. The client and host computers decide on an encryption technique from the cipher suite and generate keys and encrypt data during the TLS handshake. Excuse me. The cipher suite includes symmetric encryption techniques to preserve session security, asymmetric encryption algorithms for the handshake, hash functions to determine whether the data in transit has been altered, and digital signature algorithms. Another key exchange or key exchange is it enables two parties to use a cryptographic algorithm. For instance, before it encrypts communication that can be sent, a symmetric session key is produced during the TLS handshake. The two most important algorithms for key exchange are RSA and everyone's favorite Diffie-Hellman. Symmetric encryption, we do want to take note on that when it comes to the handshake. It's the most efficient. It's more efficient than asymmetric cryptography. Cryptography, since it transfers huge amounts of data more quickly and it consumes less resources and preserves confidentiality. Asymmetric encryption, that's basically two keys that are used in asymmetric encryption, a public key and a private key. This implies that only the matching private key can be used to decrypt a communication that has been encrypted using a public key. Because the keys are never shared and digital signatures may be used to validate data, it offers more security. Only limited quantities of the data may be encrypted using this method, and it is slower than symmetric encryption. Another important thing to note is the authentication. I can't stress enough, through authentication, both parties communicate to confirm that the other party is who they claim to be. By comparing the server's public key and the digital signature provided by the SSL certificate, the TLS handshake confirms the server's legitimacy and gives the client confidence in the server's identity. So you're probably thinking TLS 1.2, is that a bad choice, a good choice? Like, what am I looking at? TLS 1.2 is not used anymore because newer versions of the TLS protocol provide better security features such as perfect forward secrecy, stronger cipher suites, and improved key management. The newer versions also address some vulnerabilities found in older ones, including including the TLS 1.2. Therefore, it's recommended to use the latest version of TLS available whenever possible for a secure communication. And when the handshake fails, you're probably thinking, well, what happens? When a handshake fails, the connection is terminated and the client receives a 503 server unavailable error. I want to thank you guys again for taking the time to listen to some fun facts about TLS 1.2, and I'm going to hand it off to my colleague Cynthia. Thank you for your time.
Hi, my name is Cynthia Roman, and I'm going to be, or at least for my section, I will be presenting a high-level overview of TLS 1.3 while leveraging the elliptic curve Diffie-Hellman ephemeral. I will be using the acronym ECDHE throughout my presentation. So TLS 1.3 is the latest transport layer security protocol version. TLS 1.3 brings several enhancements over its predecessors, including a quicker TLS handshake and a set of cipher suites that are simpler and more secure. The introduction of zero RTT key exchanges further optimizes the TLS handshake process. Collectively, these modifications result in superior performance and robust security. As mentioned previously, the TLS 1.3 key exchange process has been streamlined to a single round trip, and this is due to the utilization of ECDHE. Now, ephemeral refers to temporary and unique keys for each session. This process ensures that even if a session key is used to decrypt past or future sessions, the ECDHE process involves each party randomly generating a public-private key pair and then exchanging their public keys. These public keys independently compute a shared secret key on both sides. And importantly, this shared secret key never travels over the internet, which enhances security. ECDHE offers several advantages over traditional methods like RSA. It provides stronger security with shorter keys, making it more efficient regarding computational power and memory. This also results in faster connections and data transfers. Implementing and deploying ECDHE for TLS 1.3 involves turning off export cipher suites and using a robust Diffie-Hellman group. Also, when implementing ECDHE with TLS 1.3, you would typically use a library that supports these protocols, such as OpenSSL. You can also test your server using tools like Qualys SSL Server Test. The Diffie-Hellman key exchange algorithm relies on using large prime numbers. The ECDHE key exchange algorithm is a variant of this approach that uses an elliptic curve problem to perform a similar key agreement process. These versions of the algorithms generate random ephemeral keys for each communication session. TLS 1.3 uses ECDHE or PSK with ECDHE, which provides perfect forward secrecy. DHE and ECDHE provides added security by ensuring past communications remain secure, even if a long-term key is compromised. Now, this is because unique short-term session keys used for each connection obtain their secret key in a way that's unrelated to the master secret key. The master secret key, or this master secret key, is derived from the long-term private public key used to authenticate the certificate. Now let's go ahead and transition to the transaction. Now you can see here that each party randomly generates an elliptic curve public-private key pair. The private key is a random number chosen from a vast range of prime numbers determined by the curve size, and the public key is derived from this private key. The parties exchange public keys over an insecure channel. Despite the potential eavesdropping, the security of the ECDHE is not compromised as long as the private keys remain confidential. Each party then uses its private key and the other party's public key to compute the same shared secret. This is done by scalar multiplication of the received public key with the resulting point's x coordinate is used as the shared secret. The shared secret is then used to derive symmetric keys for encryption and decryption of subsequent communications. Now, I'm going to go ahead and hand it off to my colleague Morris.
Okay, thank you for that brief little introduction. So next we're going to be talking about optimizing the speed and performance with various key exchanges. So we're going to explore Diffie-Hellman, elliptical curve Diffie-Hellman, and RSA. I've got to get my notes all organized. So brief introduction, RSA, which was named after its investors, Rivas, Shamir, and Adelman. It's a public key crypto system that is essentially the founding father of the TLS 1.2 handshake. And it made it the dominant choice because it is very straightforward and secure. It is very basic as well. And so moving on to Diffie-Hellman ephemerals, it is introduced by Whitfield Diffie and Martin Hellman in the late 1700s. The late 70s, my bad. And it allows two parties, each having their public and a private value, to establish a shared secret over an insecure channel. So it revolutionized its communications when this was introduced to this industry. So the problem is not all cipher suites are compatible with DHE and ECDHE. So we're going to learn that in a perfect world, these two would be the preferred communication method. But since not all cipher suites, which are about 37 of them, they're not compatible. So RSA is basically the most dominant choice for this transaction. So next, right here, we have the handshake, the TLS 1.2 handshake that we were introduced to previously. And so I'm not going to talk too much about it, but first we have the client hello, and right here it sends out its cipher suites random numbers. We mentioned this, but right about here, step 5, that's where the first handshake or the first round trip pretty much ends. So this serves as the negotiation for the parameters and how this secured connection is going to commence. So based on what type of key exchange, RSA, DHE, and elliptical curve Diffie-Hellman ephemerals, that's when the time starts to vary a lot more. So, and we're going to explore why that is. So with RSA, we have the variations. So right here, RSA is very straightforward and to the point. You can see, we're going to find out later how fast it really is. So sending off the client hello, the server hello certificates, the client key exchanges, and the cipher specs right here with the encryption of using the public key for this transaction. We're going to see how it affects the speed and the benefits and the pros and cons for RSA. Now, when we go, I'm going to introduce this slide a bit later, but now with Diffie-Hellman ephemeral, oh shoot, I'm huge. With Diffie-Hellman ephemerals, it takes a lot longer because, as you can see with all these equations, it is computationally intensive as well as very expensive in the long run. So starting off, they both sides agree on a prime and a generator, and this number is it's not a small value. It's very long. It's very long, and processing this number takes a lot of time and energy for the computer. So the generation of the private keys and the calculation, it is presented here with A equals G to the power of A mod P. So that's for this side right here. And simultaneously, the other side is going to be doing this exact same calculation. So when they exchange the public keys, you have the bottom part right here, which is K equals G AB mod P. And that is calculating the shared secret. So right here, K would equal the shared secret, but in most examples and other cases, K would be replaced to a capital S. Okay. So now variations in elliptical curve Diffie-Hellman ephemerals. I need the notes for this. Sorry. Uh, so the server generates a random key, a random private key, which is D of S, and it computes the corresponding public key, Q underscore S equals DS times G, where G is the base point chosen on the elliptical curve. And for TLS 1.2, a prime example or the basic example of this elliptical curve would be curve P225. And what I read about this curve is that it's the prime choice for the TLS 1.2 handshake, but it does cause a lot of controversy because there is some arguments that it is not as secure, it's not as fast. But the thing is, not all cipher suites are compatible with the same elliptical curve. And so, although this process is very complicated, you have the key exchange QC, finish the generation of the asymmetric keys, and the final shared secret. It is very secure. So right here we have the speed comparisons between each cipher key exchange on 2048 bits. So as you can see, RSA is the fastest, which is taking about 0.88 seconds. And so with Diffie-Hellman, you can see that huge jump from 0.88, not even a second, to 18 seconds. And when we compare it to our modern world, 18 seconds is quite the long time for anybody to be waiting. And so with elliptical curve Diffie-Hellman ephemerals, you get the best of both worlds. You get the speed and that security that I have not mentioned yet, but I will in a minute. But with RSA, you're lacking forward secrecy. And with forward secrecy, if a key is compromised from that session, you can use that again to access any future communication. So vulnerabilities with this can be man-in-the-middle attacks, and nothing good comes out of it. So with Diffie-Hellman ephemeral, very revolutionizing when it offered the forward secrecy. So you do have forward secrecy, but it comes at a cost, and the cost is time. So here, time is money and computationally intensive. So with Diffie-Hellman, the keys, the ephemeral keys, they're generated for each session, and that session, you cannot use those keys to compromise future or past communications. And same thing with elliptical curve. Elliptical curve is very complex and it's always generating the new keys for that session. So you just like Diffie-Hellman ephemerals, you can't use those keys to um, compromise the communication. So when I say the best of both worlds, you have the best time. So right here, it is a bit longer than RSA at 2048 bytes, but you do have that security, the added security of forward secrecy. So that's why it's a prime choice for most communications. But like I said, in TLS 1.2, not all cipher suites are compatible with elliptical curve Diffie-Hellman ephemerals. So with TLS 1.2, it is a very secure handshake. But the thing is, in our growing world, we're starting to transition more into like 1.3, which will start exploring into the next section. So my colleague Marco will start explaining that. And it's very interesting. He introduces us to that transition between 1.2 and 1.3 and how quantum computing may or may not impact this. So I will pass it on to him. Thank you.
Thank you very much, Morris. Like he was saying, my name is Marco Gonzalez, and I'll be talking about the changes from TLS 1.2 to TLS 1.3 as it pertains to security. So let's get to my first slide. So when it comes to changes, it's hard to address security without talking about vulnerabilities. So earlier versions of TLS 1.2 are susceptible to vulnerabilities like Freak and Logjam. 1.2 and older versions support the use of export-grade cipher suites, which are now considered weak. For example, the Freak attack exploits the fact that some TLS clients will fall back on the weaker export cipher suites. The exploit tricks the client into thinking that the weakest cipher is the one that needs to be used, allowing the attacker to decrypt the traffic between the client and the server. Now, when it comes to logjam, the attack exploits the fact that the export cipher suite uses weak Diffie-Hellman key exchange parameters. An attacker will then perform a man-in-the-middle attack to decrypt the traffic between the client and server. Now, there are some workarounds for legacy devices, or maybe people that just aren't ready to upgrade to 1.3, and that's essentially just disabling support for export grade cipher suites, but it is safer overall to just upgrade to 1.3 as soon as possible. 1.3 also has improved certificate authentication. This makes it more resistant to man-in-the-middle. 1.3 supports stapled certificates. It's a copy of the server certificate that is sent through the handshake. This helps to protect the client from man-in-the-middle attacks. It does require the use of certificate transparency, which publicly logs all TLS certificates that have been issued. This makes it harder for attackers to obtain fraudulent certificates. In addition to those protocols, 1.3 uses a certificate protocol that is more resistant to man-in-the-middle attacks. SNI, or server name indication extension, allows the client to tell the server the host name that it's trying to connect to. This helps to prevent the attacker from impersonating the server. We also have improved session resumption. This allows the client to reuse session keys from previous connections, which can avoid the need to perform a full handshake. Now, this does speed it up, but it also makes it more secure. So during 1.3's use of session resumption protocols, which is called ECH, or encrypted client hello, it allows the client to send its session ticket to the server in an encrypted format. That helps to secure that connection. This helps the ticket from being intercepted by attackers. So overall, the new resumption improvements help improve the security as well as the performance of TLS connections. Lastly, we also have zero RTT key exchanges. Zero round trip time allows the client to send application data to the server without having to wait for the full handshake to complete. This is how 1.3 is able to reduce latency by about one round trip. Now, this is only possible when the client and server share a PSK, or pre-shared key. I'm going to move on to our next slide. Here we're going to talk a little bit about how quantum computing affects security. So in TLS 1.2, older versions of Diffie-Hellman were vulnerable to Shor's algorithm. Shor's algorithm is a quantum algorithm. It's the fastest known algorithm for factoring large integers. TLS 1.2 uses RSA encryption, which relies on the difficulty of factoring large integers. Now, if a quantum computer was powerful enough to implement Shor's algorithm, then it could potentially or eventually break TLS 1.2. This is still in its early stages, and we don't know when a quantum computer will be made that's powerful enough to run the algorithm properly, but it is something that we're worrying about in the near future. Now, when it comes to TLS 1.3, we've improved that by improving and changing the cipher suite. 1.3 uses something called ChaCha20-Poly 1305. ChaCha20 is a cipher suite that is supposed to be resistant to quantum attacks. It's a post-quantum cipher suite that is resistant to Shor's algorithm. ChaCha20 is a stream cipher. It's faster, it's more secure. Poly 1305 is an authenticator that's used to protect against data tampering. Now, alongside the cipher suite, we also use post-quantum algorithms. We touched on these a little bit in the first slide, but just to kind of review, they should be used alongside ECDH to protect against quantum attacks. So some of the ones we touched on were encrypted hello. It encrypts the client's hello message. It protects the session keys from being intercepted. We also have post-handshake authentication. This allows client and server to authenticate once the handshake has been completed. This helps to protect against man-in-the-middle. We also have forward secrecy, which is it was supported in 1.3, but it's now required in 1.3, and it's been improved on, and now it's perfect forward secrecy. This ensures that the session keys are not compromised, even if the server's private key is compromised after the session has ended, protecting the traffic that was sent over previous sessions. So we're going to take a look at the handshake transaction, how all of these just kind of work together. And we've already talked about them, but we're just going to really talk about the security aspects of it all. So we already know that it's a faster handshake. So it starts with the client and the server both saying hello, but in 1.3 we encrypt the hello with ECH, which allows the server to process the handshake immediately. 1.3 also removes the certificate request message and the new session ticket message, reducing the number of round trips required to complete the handshake. So this is how we're speeding it up. But the security part of it is that it supports early data. The client can send application data before the handshake is complete through the use of encrypted client hello. So the server is then able to start decrypting the application data found in ECH. 1.3 support of session tickets also allow the server and the client to resume TLS sessions without having to perform the full handshake. We've improved the cipher suites. These offer for better protection against known future attacks. It requires the use of post-quantum cryptography, so we're implementing that as well. That's what's making it more secure. But alongside that, it's also more efficient. It's able to be processed more quickly by CPUs, which improve performance. They're also a lot simpler, making them easier to implement and maintain. So we talked about forward secrecy, but in 1.3, we have perfect forward secrecy. So 1.3 only supports ECDH. It also uses a new exchange key algorithm called Curve 25519. This is a post-quantum key exchange algorithm designed to be resistant to quantum computer attacks. So with perfect forward secrecy, it leverages the ephemeral elliptic curve Diffie-Hellman, or ECDHE, which is more secure than PFS, which is used in Diffie-Hellman. 1.3, the server also signs the entire handshake transcript. 1.2 only signed the certificate verify section of the handshake. So signing the whole transcript allows the client and server to verify each other's identity, but it can't verify the integrity of the entire handshake. So we're looking to resolve that by just signing the entire transcript altogether. 1.3, I'm sorry, that's pretty much it. So we're remedying that by signing the whole handshake. So it's going to make it more secure. It prevents man in the middle, and we're improving security by making it more difficult to tamper with. So those are really just some of the big major changes between 1.2 to 1.3. So we're going to go ahead and move down to our next section. So I'm going to hand it over to Sunny. Thank you.
Hello, everyone. My name is Sunny. Just like my colleague said, up until this point, we have all talked about the encryption, transaction, handshakes, and other related things when it comes to cryptography. But as we're stepping into the future with technology developing faster than ever, we're about to take a peek look into the future of encryption, and also we'll be discussing about things related to quantum networking. So here we go, which is my first slide, unveiling the future of security. An in-depth exploration of emerging encryption technologies diving into homomorphic encryption, zero-knowledge proofs, and the intersection of AI and cryptography, where we would be discussing about the application, basic applications, basic introduction, and the complexity of each aspect with its developing nature. Encryption is a very involving field, continuously adapting to changing the technological landscape. Overview of the three advanced technologies shows that the promise in enhancing the data privacy and security. So looking at here, first we will be talking about homomorphic encryption. This is something that enables computations on encrypted data, producing results that, when decrypted, align with operations on the original plain text. Some of the applications that we could see for this aspect or this technology developing is secure cloud computing, which offloads computations to a cloud confidentially, maintaining the data privacy. The privacy preserving data analysis would help analyze the data without exposing sensitive information, ensuring the user privacy. Secure voting systems would help in a way that safeguard the integrity of the voting results, preserving the voter anonymity. But as we all know, these things do come with the challenges that we'll have to face. Performance, computationally intense, required a significant amount of resources. Complexity is demands in-depth knowledge and demands in-depth knowledge for effective implementation and use. Moving forward, we have so moving along, friends, we have zero knowledge proofs, which is another developing thing that we will be seeing in regards to encryption as well as cryptography. So a cryptographic approach where a statement's truth is validated without revealing any additional information. There are basically two types of zero knowledge proofs that we can see: the ZK snarks and the ZK starks. The ZK snarks are Susian and non-interactive proofs offering efficiency, whereas the ZK starks are offering scalability and transparency without needing a trusted setup. Applications for each of them are blockchain and cryptocurrencies. Cryptocurrencies enhances transactional privacy in cryptocurrencies like Zcash, where secure identification where secure identity verification helps to authenticate the identities without exposing the sensitive credential information to any unrelevant party. Challenges with these new techs, like I said, always we're gonna have some challenges that will be faced by our team. So when we're looking at again the complexity for the zero knowledge, the ZKPs or the zero knowledge proofs, we are able to see that the high design implementation and demands. The computation cost for these process certain for these certain types can be very expensive and may not be very effective in some or the other situations. And here now, everybody, that's what we've been waiting for: AI and encryption. So as we all know, this in 21st century at this age, we're actually rapidly exceeding everything. We're rapidly exceeding our integration, AI integration into our real world. And so the same way, encryption and cryptography are nonetheless, they are also intersecting with AI. Secure AI models help to safeguard machine learning models, especially in decentralized learning environments. This also helps in privacy preserving, where an AI enables the model training on sensitive data sets without compromising the data privacy. But again, these are the same factors where these technological advancements do come at a challenge with challenges and complexity. And then for the AI, we are about to see some of the challenges. So one of them is adversarial attacks, the potential misuse of AI in creating sophisticated threats. The resource intensity would help to merge. These helps to merge the use of AI and cryptography can be resource intensive, which again becomes very expensive and ineffective at the point where at this current stage, it looks totally nothing but just a hope as we move or take a step forward in the future. To conclude with these three, I would say emphasizing the intertwined future of encryption with technological advancements, notably in AI, highlighting the continuous innovation necessities encryption to navigate the dynamic digital security landscapes. Um, I would also like to touch base on, this is a freebie that I'm going to add. We'll be talking a little bit about the quantum networking and the encryption that we'll be seeing. The things that I would like to mention here is breaking public key crypto systems. Quantum computers can efficiently solve the mathematical problems underpinning the RSA and ECC, rendering these crypto systems insecure. But the question is, are we going to be needing any kind of cryptography or encryption in future when we're talking about quantum networking or computing? From my best of my ability and knowledge, I would like to share that yes, we would still need it. If widely used encryption algorithms are broken, it could compromise the confidentiality and the integrity of the data transmitted across the network. Some of the opportunities for encryption that we see post-quantum cryptography, this branch of cryptography would be focused on developing cryptography algorithms believed to be secure against quantum networks or quantum attacks. Sorry. Algorithms being developed under post-quantum cryptography include lattice-based cryptography, hash-based cryptography, code-based cryptography, and multivariate polynomial cryptography. The necessity that we see the necessity of encryption that I would say in the quantum era is all about protecting data. Encryption will be still essential for protecting data confidentiality, integrity, and even in the era of quantum computing. Securing communications, right? As we talk, the securing when we are all about securing our information, securing our communication, right? In a quantum network, the cryptography tools such as QKD could be used uh, secure communication, ensuring the transmitted data remains confidential and secure from eavesdropping. Authentication and verification. These two will be the great protocols. No, I'm sorry. These two would be still necessary for cryptography protocols to authenticate users and verifying the data integrity in various applications, including secure communications, financial transactions, and data storage. I would like to conclude my data and my topic here with encryption and cryptography will remain ever crucial in the era. However, we move in the crop. However, we move in a landscape of cryptography, we will need to evolve and adapt to the new reality and the quantum world. Researchers and industrialist professionalists are already working on the post-quantum cryptography algorithms and quantum cryptography protocols to ensure the security of the data in the quantum future. Adaptation to quantum resistance cryptography algorithms and protocols will be essential for maintaining a security in a post-quantum world. And with this, I would say thank you to all my colleagues for here sharing all their thoughts about today and making us aware about this information that we had in front of us. Please I would like to again thank you, Cindy, Cynthia, Marco, and Morris for all their bright and brilliant knowledge that they were able to share with us today as a team, and hope this all helps you guys. Thank you, everyone.